Good morning and welcome to the amazing presentation about QEMU running in UEFI. Who knows what QEMU is? Who knows what UEFI is? This is exactly the right audience, perfect. So who am I? I'm Alex Graf. I'm officially a KVM and QEMU developer, but I also do a lot of ARM things, as you might have heard. My whole QEMU and KVM background is on a lot of fancy things like running nested virtualization. I was the first one to actually do that on AMD CPUs back in the day. I did the server class PowerPC KVM port. And I'm also the U-boot UEFI maintainer now, where you can basically run UEFI applications in U-boot. So I wrote that one. Essentially, it's always, the basic pattern is if people think it's weird, it's me. So, what's our problem? So imagine you have two systems. One is an ARM server, one is an x86 server. And now you want to plug in say, a graphics card into each. And you start them up, and what happens? Well, on your amazing x86 server, you obviously see an operating system booting up, and everything looks and feels the way it should. Whereas on your ARM server, you just don't see anything. The screen stays black because that graphics card never gets initialized. Why is that? That is because the graphics card actually contains the driver for initializing that graphics card and making use of that graphics card on itself, and that driver is usually usually comes along with the graphics card as x86 binary code, and we just can't run that on ARM, right? So a while back in Budapest, Art and me sat down together and we brainstormed for a while and tried to figure out whether there is a solution to that, and we eventually came up with exactly that one. As an interim step to enable people to actually run that x86 code on their ARM systems. But why is that an issue in the first place? So, if we look at the difference between ARM and x86, this is a nutshell and really high level. So if you know more than, if you already know the difference between x86 and ARM, ignore those slides. But this is, if you don't, that's a really easy overview of why they are incompatible. So imagine you usually have registers. Registers are something where you just store values in. And if you even look, like from a 10,000 feet point of view, if you look at the difference between x86 registers and ARM registers, you can already spot there's a difference, right? You don't have the exact same number of registers, they're called differently. Things are just slightly different even on that level. Say you want to copy something, a value, from one register to another. If you look at the way this works in binary code itself, we call them opcodes, then if you want to copy something from one register to another, from x0 to x1 on ARM, it looks like this. Over here is the encoding that the CPU actually reads. This is a hex value. Whereas on x86, you essentially get that. They don't look any way alike, right? You can't just go and say, oh, well, it's just a different language, let me try to map one on the other. That's really hard to do. But that's exactly what QEMU does. So QEMU essentially gives you a nice way of taking one CPU language and converting it into another CPU language, in a nutshell. So what is QEMU really? QEMU has a couple of different modes. QEMU, obviously, you know QEMU, I mean, you just said so, emulates your machine, your computer. But what part of it does it emulate? So we usually have a couple of different layers. You have your hardware, you have your operating system, and then you have software running on top of the operating system. In the most common and most well-known use case, QEMU emulates its full systems, which means you put all of these pieces into the matrix, essentially. So you make all of them virtual. You emulate your hardware, you emulate all components of your hardware, you emulate your IDE controller, you emulate your whatever, your CPU, you emulate your operating system that basically runs on that CPU because you're emulating the CPU, and because of that you're also emulating your user-space applications that run on top of that operating system. QEMU has another mode called Linux user emulation, which essentially provides a bit of glue between the user space interface and the kernel interface and the translation layer to convert between the two, so that you can run, say, x86 applications on ARM or ARM applications on x86. But that's on the application layer only. Those are the two modes that are in the QEMU tree today. You can just grab them and use them. But what we're trying to do is we really want to just run UEFI code emulated. But where does that fit in those layers? So you have the hardware, you obviously want to run on real hardware, so we don't want to emulate that one. But we do want to emulate some chunk of whatever UEFI is. But who actually knows how UEFI works internally? That's the answer I wanted to hear. Perfect. So what is UEFI? UEFI basically is the thing that initializes your hardware sometimes, not always, and then allows a generic boot framework to boot from it. So imagine you have a computer, and the computer has hardware attached to it, like a storage device, or say a graphics card, or some network connectivity, or some CD-ROM, any hardware, any connectivity to the outside world that is available. UEFI has drivers for those, and then provides a generic interface that everybody can use, every application then could potentially use to access these devices. So say, for example, you want to run Graf. This is the Graf mascot. They disclosed that on last year's FOSDEM, the year before last year's. Say you want to run Graf, and you can basically load Graf from the disk that way, and then have Graf actually talk to the disk and load, for example, Linux from that disk and execute Linux. And what usually happens is that once you're in that step, you basically have a switch from what we call boot time services to runtime services, where most of UEFI disappears. All those drivers, they just get thrown away, and you're only stuck. The only remaining part you have are the runtime service chunks of it. So really small stuff that allow you to access hardware from while Linux is running. So let's take one step deeper down into how UEFI works. So when you have this driver, so imagine I have a disk driver. What the disk driver does first is when it gets loaded, it needs to register itself with the whole infrastructure. So it does that by calling a global service. And into that global service, it passes a struct that contains function pointers and just normal properties, normal fields, random numbers basically. All the contents of that basically gets stored in a global context so that you can later on make use of it. And then when you have a card plugging in, something that can make use of that driver, the PCIe driver, for example, registers a handle for that card in the global context again, and then the UEFI framework goes in and tries to match whether the new card is supportable by the driver that was just registered before. Does that make sense? So for a concrete example, say you have an HCI controller driver and an HCI PCI device, then you first register the HCI controller driver, and then the PCI driver comes in and creates a device entity for the HCI PCI device, and then those two just get linked together, basically. When they get linked together, what happens is you basically just call start, the function pointer again that was passed in earlier by the driver, which means you're back in the driver now, which can then do things on top of that disk that you just enumerated. For example, it can go in and install another protocol. For example, a block protocol, so you can read and write data from that disk, which again is a struct that has random fields and function pointers. Do you remember how the old struct looked like? That had function pointers in the beginning and then fields. That one has fields somewhere and random function pointers somewhere. You have no idea what each field means unless you know exactly what the protocol does. So it does them, then Graf can go in and say, well, I would like to read some data. So let me go and find that block device driver, the block device protocol, that's what they call it in UEFI speech. Let me go and just read some data from that UEFI backed device, and let me read some data from that UEFI backed device, and I can essentially read any data from Graf. That's exactly the way Graf flows and works. Now, if we want to put that driver into a virtual environment, the problem we have is that our structures obviously look different between architectures, right? So imagine you have your structure that registers for the block protocol, and you look at just the hex dump of what all the contents of this is in memory. Then you see the U64, the revision that's just up here, it's a 1 in little endian. Then you see a pointer, and then you see a couple other pointers. That's the way that it gets represented in memory. The really nice thing we found out basically in Budapest is that that structure is actually, thanks to ABI compatibility, the same between AH64 and x86-64. So we are both little endian, we both align the same way, everything basically looks the same in that structure. Now, imagine a structure like that, right, where you have a 32-bit number and then a 64-bit value, which basically is a pointer. The x86 ABI defines that when you have 64-bit values in a struct, they need to be naturally aligned, which means you need to start a 64-bit value at a 64-bit boundary. So what happens is that you basically get padding in your structure, right? These values basically just don't mean anything. You have your 1 here, and then you have the pointer exactly 64-bit after the initial value. Well, the good thing is the ARM guys were actually pretty smart when defining the ABI and did the same thing. They are fully compatible. Like in the alignment, in the way they look, in memory, everything looks exactly the same. So all the structures, all the data pieces of your driver that would run in x86 or in ARM are just completely interchangeable. Each of them have the exact same view on what is represented in memory. Make sense? Oh. Yes.
For the different ending, is the same?
So the question is it the same for different endianness? UEFI specifies it has to be little endian. So that problem is solved.
Well, it does for those architectures.
So now imagine we would put our structure into something that is virtual, into an emulated context. How would an ARM binary go in and call that x86 function? I mean, if we just basically take those functions, function pointers, say, imagine we could just execute the registration routine from our x86 code, and it registered those structures. How would we be able to tell that the code that we're actually trying to execute is x86 code and not ARM code, and just execute it as ARM code, which looks very different, you saw that earlier, from the way x86 code was. So for that we need to dive into how function calls actually work. So imagine you have this function call there, just the read function again. What that does is you basically on your ARM system you have a couple of registers that get used for register passing, for argument passing. And what the C compiler does is it basically takes all of the arguments you have in your function call, it puts them into different registers, so that the called function can then fetch them from the well-known registers again. That's essentially what the calling ABI means. What happens then is you also write something on the stack, namely the return point. No, the return point is not in there. There's something on the stack, I forgot what. You put something on this, or you overflow registers on the stack if you need to, and you put your frame on the stack. And then you essentially call, you change the program counter with the read function pointer. So you just jump in there and also change the link register. Now if that code is x86 code, you would basically end up executing invalid machine code. the trick we came up with is no execute. Who has heard of no execute? It's an amazing crowd, awesome. So no execute is a security mechanism. We're abusing it, but it is in its original form a security mechanism that really gets used to declare that regions usually would be readable, writable, and executable, but with the no execute feature you can say, well, I have this special region here that, yeah, you can read and write it, but do not execute any code. If there is any code execution inside that range, throw an exception, tell me that something went wrong. Usually you use this for stack protection and data protection. So if you have a user space binary and you want to make sure that a buffer overflow on the stack doesn't result in in code execution, because somebody could just write random data on your stack, which could be opcodes, which again could be executed. You declare your stack as no execute so that people don't jump into it and just run code. We can use the exact same feature to declare all x86 code as not executable, which means if we now have our program counter programmed to be x86 code, instead of executing invalid machine code, we end up getting an exception. Well, exceptions are nice because now we have control. And in that control, we can just pass things into our emulation layer. What does the emulation layer have to do? Well, turns out x86 also has a function called ABI. So you have to define it somehow. And that means we need to now go in and map all of those values that we put into our ARM registers into our virtual x86 registers. The function ABI looks a bit different, but you basically get the same thing. And you also need to overflow things on the stack, and on x86 on the stack you also need to put the return pointer on, where you just put a canary that says when you return to your caller, you don't really return to the caller, you return to the emulation exit. So we basically just go in, modify our stacks, go run it, and now we are in x86 context. So we chunk on, we execute our whatever code, our x86 UEFI code, until we end up hitting a function call that gets us back into ARM, right? So what would we do there? Well, how do we know that even? Well, the answer is very simple. We always do know, because we know where our x86 code lies, and we just simply assume that every code outside our own x86 code always has to be ARM code. Because if it's not, and we call that code using the ARM function called ABI, and it just happens to be MIPS code instead, the MIPS emulator would kick in and do the same marshalling again. So what we do is we realize, oh, there's a function call going to ARM code, so it's outside our range of handled x86 code, so we marshal everything back. We take our registers, you have the exact same thing, just in reverse. You basically take all of your values from your x86 virtual environment and put them all back into registers on the ARM environment. So you marshal all the function called ABI back and move on. Make sense? Awesome. It's not that great yet. There's more to come. Don't worry. So what that means is you can essentially have an ARM Graf binary calling into x86 network functions, calling into the ARM UEFI core to say allocate memory. So you get emulation on function call boundaries. You don't have the boundary of hardware accesses, which is full system emulation. You don't have the user space emulation boundary where it's syscalls. This is on function calls. Now the big question is, does it work? Yes, it does. This is me in front of a Seattle system showing Graf displaying stuff on the monitor using an AMD, I think in this case, AMD option ROM that was really just on the card. I plugged in the card, booted it up, and it just worked. If you've done any of the sync racer demos, they all ran that code. Every time you plug in the GPU there, it's always running through the emulation, and it just happens to work. Now, why did I choose QEMU? Well, you saw the initial slide that I kind of know the code base. But there are more reasons. It actually has a couple of very nice properties. It's written in C, which is very important. I was looking at Box as an alternative, and Box is written in C++, and I really don't want to have C++ code and exception handling in my firmware code. It's very isolated, so the tiny code generator that is part of QEMU was originally made for a completely different project. It was made for a C compiler that basically compiled your kernel on boot up. So your bootloader would just call into the compiler at a bunch of source code and would compile your kernel every boot up. Tiny code compiler. It is LGPL, so every piece of code in there is LGPL, which means you are very likely to get into licensing issues. Very unlikely to get into licensing issues. Modern QEMU is GPL, but other emulators also are basically GPL. For 32-bit x86, it's very easy to find emulators out there. For 64-bit x86, it's close to impossible. Another question I always get is, why don't you just use EBC? So what is EBC? EBC was an idea from Intel back in the day when Itanium was hot, that they needed to have a single option ROM and basically a single binary unit option ROM to run on all of their platforms, on their x86 platform and on Itanium, and later on as well on x86 64. So what you're getting is bytecode that essentially is bitness agnostic, so you can have the same bytecode running on 32-bit and on 64-bit platforms. And it does all the structure padding and such magically. That one was shipped in option ROMs until around 2005, from what I can tell. Modern cards simply don't have it. The problems with EBC is that the compiler these days is completely unsupported. Intel does not care about EBC anymore because they don't have Itanium, so why would they bother? Microsoft refuses to sign EBC code, which means if you put EBC code into your option ROM and you want to do secure boot, tough luck, it will not get signed, Dave.
And will Microsoft hand you the x86 signing key for your ARM systems?
So the next question is, will Microsoft hand you the x86 signing key for your ARM systems? I don't know, but it's definitely, at least you only have one entity that you need to convince at one given point in time, and not 50 to use a different key if you wanted to not use the Microsoft key to sign your EBC code.
Yeah, my point is that there's no real benefit in that point. I don't acknowledge it as a benefit because you still have the problem that you don't have anyone agreeing that your option ROM is signed.
Is it not just an x86 signed option ROM, and those keys, the public keys are, is there not any problem? What's the problem with taking the existing Microsoft x86 keys and putting them into the ARM?
The problem is the guarantee that when Microsoft ship systems, are they going to use the same keys on their ARM systems? Or do we not care?
Okay, you're getting, that's, why don't you keep going? Because
Yeah.
I think that's a side conversation.
Let's solve the signing part later on, but I really don't see a big issue with it.
Yeah.
Whatever you do, you're not worse off using emulation in that case. If you have bugs, say for example, we found a really nice one on NVIDIA. So the NVIDIA graphics driver, at least the one we looked at, has a bug where it basically has a function that tries to return a pointer to a common, like a PCI device specific struct. So it loops through a list of known graphics card PCI IDs and then returns the pointer to the struct when it finds them. And when it doesn't find any in the list, which it doesn't for every other card in your system, because it's only your graphics card actually has the known PCI ID, then it basically returns null. which means now you have your caller that would need to check whether the return value is null, but they forgot about that. So they just dereference that null pointer, which is a really bad idea when you have a system that does not have any memory at address 0. So these bugs will be the exact same if you compile them as EBC code, as native code, as it doesn't matter what type of code you have. If you have a bug in there that makes it not follow the normal specification but takes assumptions that are platform specific and not ISA specific, they will still break the same way. And since nobody's doing EBC today, you would have to convince everybody to then port into EBC, but they will still want to support the x86-64 option ROMs as native code because they're faster and better and more amazing. So you would still have 2 option ROMs in there, one for x86 and one for ARM, so you didn't actually win anything, because really what you should do is run native code. So instead of convincing people to use bytecode to interpret things, just convince them to use native code and you're good. But for native code, we obviously always want to run native code whenever we can, but sometimes you happen to have a network card or a PCI, like any random PCI card in your shelf that just is not the right SKU. It does not happen to have ARM option ROMs in there. So using the emulation, you can at least see if that happens to make the adapter work. So you're enabling devices that simply wouldn't work otherwise. So now that you're so hyped up about the whole emulation thing and you really want to try it out, how do you use it? Well, the easiest way to use it is to go on Art's GitHub page, where he hosts all the things, and run these few simple instructions. They're in the README on that Git repo. Basically, it's just checking out EDK2 and building it with an additional option with an additional optional module, which is the x86 emulator module. And that, as a result, gives you an EDK2 version for QEMU that contains the x86 option ROM emulation, which I can show you.
You're cheating a little bit on the make of EDK2. That's not that simple.
Can you read this? No. No. Can you read this?
That's better.
All right. So this is running an EDK2 version that does not have the x86 emulator on there. What I'm doing, oh, actually I was missing one slide. The demo setup. So what we're doing is we're running an ARM virtual machine in QEMU that runs our ARM UEFI binaries, EDK2. And in that virtual machine, we plug in a V1000 adapter because QEMU can just emulate them really well. But that that E1000 network adapter by default obviously has an x86 option ROM, since that's what E1000 cards have. The whole thing came from Intel from the first place. So usually you wouldn't be able to see any network code, and that's basically what I'm showing there. So here you can see that while we do see our E1000 network adapter in our PCI enumeration, you do not see any network adapter discovered by UEFI because there's simply no driver for that PCI adapter that UEFI can execute. So if we now use the binary that contains our x86 emulation, we can run the exact same environment, but now you can see that it actually starts PXE over IPv4. So it's discovering our grub that is stored on there, which is an ARM binary, which shows us a nice installation screen, and we can keep rolling. This is grub calling into x86, into an x86 option ROM, handling the E1000 adapter, running in QEMU on an x86 system, but that's a different story. This is emulation, but it works. Woo. All right, questions? Grant?
So the gotch, there's always gotchas with going to the emulation. Yeah.
Do you want to have a microphone?
I got one right here actually. I just put all my stuff on top of it. Where are the corner cases? So, you know, I'm a big supporter of the approach and doing things in this way to just for enablement. There's always going to be a little bit of, you know, where are the problems that you see? Where are the corner cases that we need to be watching out for if trying to run x86 option ROMs?
They're actually really simple. So that's the bug category I was talking about. There's more to x86 than the ISA. So there are a couple of assumptions you can make on x86 that do not apply on every ARM system. And if your code happens to take these assumptions, it will break a native code as well. But if you're doing a native option ROM, you also have a native QA process after that option ROM building, so people will plug it into real ARM servers and realize that their code is broken. Whereas before they just didn't, since they didn't plug them into ARM servers.
Right.
All right.
Yeah, so I can add to that. So these are all PCI drivers by definition, right? Because they're PCI option ROMs.
Yeah.
And what you see in the Intel systems is that they, well, basically they don't use the PCI protocols correctly. So on an x86 system, you can just malloc something, take the CPU address, which is virtual equals physical on UEFI. So and you take that address, you just program it into BMA registers. Just works just fine. You don't need to unmap do the whole PCI dance. Another thing, so there's always memory at 0, which means you can dereference null pointers, but it also means none of these drivers bother to enable 64-bit DMA.
Right.
So on my Seattle overdrive, there are things that don't work, not because the hardware doesn't support it, but the driver doesn't bother because you don't need to on a PC platform.
Right.
Another question on x86 option ROMs. For option ROMs that end up now having runtime services components, are those supportable? Or are there any that would matter?
Easy answer is no. And the actual even more verbose answer is our framework essentially makes sure they don't load.
Okay.
So that you don't by accident happen to have a runtime service that really contains x86 code that your kernel now tries to natively execute.
Right. Are there any cases that you know of where that is a problem of not being able to do the runtime services code?
I'm fairly sure if you want to run Windows 10 on your system and you have a network adapter that is not supported by Windows but relies on the fact that it needs to download the driver from the internet first, which means it needs to access the NDIS driver using runtime services.
Right.
That will not work.
Right.
In the Linux world, I don't know of any case where we would actually provide a runtime service or make use of a runtime service driver as that would be implemented by x86 code.
Right.
At least not yet. Maybe somebody's going to write an NDIS driver sooner or later. Today it doesn't exist.
Okay. I'm done asking questions.
Anyone else?
You handle calling function pointers that have arguments passed on the stack as
Yes.
well?
Yes.
How do you know?
We can just assume there are always at least 16 arguments that we may have to handle and just handle them. I mean, if we overread the stack to the back, we know we are always reasonably deep into the calling chain, whatever happens. So reading a couple values beyond our return stack part is not an issue.
Okay.
So obviously performance here, I'd assume isn't, it's not normally going to be a priority, but how
Close to
slow is
native.
this?
Close to native.
Wow.
This is actually a JIT running. This is not interpreted code, this is not slow, this is an actual good JIT executing the x86 code, which also does not do a lot. So that x86 code doesn't have to handle a lot of pieces, because it's calling a lot of UEFI functions around it to do things like menset even, because that was born back in the EBC days when EBC was slow. Right? So people still have those calls in their function writers sometimes. But even then, I mean, even a memset is not slowed through the emulation because it's fully jittered.
How feasible is it to port this into U-boot as well?
Porting that particular part into U-boot is easy. The problem is that your drivers are going to call a lot of interfaces that are just not implemented on U-boot at all. I mean, if you, the first step to having that would be to make a native driver work. Say, take iPXE, compile it for ARM, and then try to make that one work on U-boot first. And if that works, you can try the x86 version of it.
Right.
I'm wondering that, I mean, I'm surprised one question did not come up. Is this upstream? The answer is pretty simple. We actually, at FOSDEM, one of the EDK2 maintainers said, well, just submit the code, it's fine. So the only blocking thing is somebody having time to actually push it, which essentially boils down to me. So I didn't get around to do it until now, but the code, the basic code, the framework will be upstream sooner or later, and the emulation package will hopefully go into Leif's non-license compliant package.
So what does that? What's the implications for someone shipping the firmware with the LGPL block?
Well, I don't think the LGPL is the interesting one for someone shipping firmware. I don't think it's the LGPL thing that's the problem for someone shipping firmware. I think it's the, oh look, we're shipping firmware that's emulating x86 that's going to get their legal department really wound up. The only reason that the LGPL bits cannot go in the main repository is basically that there's a blanket rule that everything in here is BSD compliant, or else all of the legal departments of all the companies involved in EDK2 development need to go back and make a new agreement, and that's just not happening.
Yeah. Legally, it should be completely fine to emulate x86 code, and thanks to Microsoft, we actually have a really good case of somebody paving the path for us. So if they don't get sued,
I'm not saying it couldn't happen. I'm saying that. All I'm saying is that you're using the word "should" in your communications with a legal department.
put it differently, these patents, the patents that AMD has in that case, because that's actually 664 only that we care about, the patents that AMD has only apply to circuitry and not to software.
If you can convince them, I'm happy.
Can it be compiled and loaded at runtime as a module?
Yes, it actually is.
So it could be just plopped down into
yes.
the ESP.
If you have the emulator framework available, I mean that's the hard part, right? You need to have the core parts available. Artists unhappy. If you have, you still need to have the core parts available, the whole framework around it to be able to plug it in, and then you still will not actually rerun the optional enumeration. So everything that was plugged in will not get executed because your point in time of inserting the emulator will be after the optional enumeration. But I mean that probably can be worked around.
Yeah, because I could see that. I could see that being valuable from a deployment perspective of to not ship the actual emulation, but to have the framework set up in such a way that it can be put down at runtime, either in another firmware partition or some mechanism, and then you do the rerun. For deployment, that would be interesting.
Yeah, so the way it's currently implemented, so this doesn't actually work. So you have you have the boot options, you have the driver options in UEFI, which are things that are loaded as drivers before it tries to dispatch any boot options. So that would be the natural place to put it. But I mean, because UEFI or EDK2 is such a big bag of little modules that get dispatched using some fuzzy logic, and so there are some DEPEX, it's what they call DEPEXs. There's some DEPEXs, so you have the right architectural protocols. installed before you can actually start using this module. This module, but the way the PCIe bus is enumerated, because that's when it goes over the option ROMs, then it tries to decide, hey, is this something I can support either natively or via an emulator. That currently happens before the emulator is there, so that doesn't work, and that requires some non-trivial plumbing on top of the hooks. And so technically it's not an issue, but you have to sell it to the project. If we want these hooks upstream, we have to sell it to the project that this is actually changes they should be taking to accommodate this emulation framework.
How many different Option ROMs have been tried with this emulator?
We tried NVIDIA graphics cards, we tried AMD graphics cards, and we tried the iPixie ones. I also tried an Connectix 4 inside of a KVM virtual machine, but it didn't work, but I wasn't really sure whether that's because of my device pass-through or because things were just plain broken, I don't know. But that was iPixie as well, so I don't see why that wouldn't work. I think it really was emulation issues, or virtualization environment issues. You're more than happy to, I'm more than happy to see you or anyone else try more cards. And if you see bugs, we're happy to fix them.
Let's have a blog fest.
Yes, do the UEFI platform. Isn't that next week? Yeah, take it along. All right, any more questions? Well then, thanks a lot.